trigonometric term you want, or cosine or sine, but everything is relative to some phase. So cosine and sine are equivalent as long as everything's consistent. What we have here is v of t is the real part of some complex exponential expression. We could write that as v naught e to the j omega t plus v. So if we apply Euler's law to what's in the parentheses, take the real part of that, we wind up with v naught cosine omega t plus v plus j sine omega t plus v, close bracket. This is applying Euler's law. And we take the real part and we're left with exactly what we have at the top. V naught cosine omega t plus v. And so this is our polar representation. We can write things as v of t, v naught cosine omega t plus v. And again, just to rewrite this is measurable. Or we can write v of t equals v naught e to the j omega t plus v. And that's, oh, sorry. Yeah. Yep. And that's polar form. And these are equivalent. These all have to be equivalent. To get from the polar form to the trigonometric we just saw, we take the complex exponential. Now, one of the things we discussed in the last class is we can write this as e to the j phi, e to the j omega t, by just writing out the exponential in two terms by exponential relationships. They add, arguments add. And one of the things we indicated is every term has the same omega. So if we look at voltage in a given circuit for a given source, the voltage across the capacitor, voltage across any resistor, any capacitor, any inductor, all is going to oscillate the same frequency. So no matter what, once we set the frequency of the source, once source frequency is known, then every component V and I oscillates at the same frequency. As such, we can take advantage of the fact that everything has the same e to the j omega t term. So once we start looking at circuits, everything has this e to the j omega t term, and we can now consider this implied. And so we have a third way of writing things. V naught angle phi. And so all three of these are equivalent. And here's the same phase. Here's the same amplitude. But in this case, the e to the j omega t is implied. So all three of these representations wind up being the same thing. Largely, we're concerned, or we're going to use the phasor form in our analysis, and ultimately go back to the measurable form without going through the polar, because we don't really need to write that. It's an intermittent step. We can go directly from here to here, recognizing there's our amplitude, there's our phase, and we know omega based on whatever the source is. And if we have multiple sources, that means we have multiple frequencies in our circuit, perhaps. And so that's what we're looking at. These are the three forms. Again, just to summarize them, V naught cosine omega t plus V, V of t, V naught e to the j omega t plus V, and V of t equals V naught angle phi. These are all equivalent. Different ways of writing the same thing. And we're going to use this one to do our math. With a small adjustment periodically. This is equivalent, this guy, equivalent to e to the j phi. Remember our e to the j omega naught, or omega t term is implied. And so we can also write this as v naught cosine phi plus j v naught sine phi. So we have a rectangular form of writing our phasor expression. This is the phasor form. I had that on the previous page. That's phasor form of a complex number. This is rectangular form of a complex number. And we saw that in the lab yesterday, so should be a little familiar. Different ways of doing the same thing. Both are complex numbers. We've done this before, but in our imaginary real plot, this is VR, and this is V imaginary. And so if we did real and imaginary, and I tend to draw things in the first quadrant, but they can be in any quadrant. Don't get used to that. There's V imaginary. And then this length is V naught. And this angle is phi. And these are these terms respectively. And again, that was in the lab. You have a nice table that walks you back and forth between the conversions. And we can rewrite that out again. V naught equals VR squared plus VI squared, square root, that's the Pythagorean theorem, and phi equals tangent minus 1 VI over V real. And again, this was all in the lab. The thing to be careful with the inverse tangent is the reminder I've mentioned several times already. Be careful what quadrant you're in. So know what quadrant you're supposed to be in. If you wind up getting a result that's in the wrong quadrant, you're probably off by 180 degrees because the third quadrant and the first quadrant on most calculators give you the same result. And likewise for the second and the fourth. And on that note, we can do some little quick mathematics. I gave you a little handout, some various complex numbers. A equals 4 plus J4, B equals 2 minus J2, C equals minus 3 minus J. And so, typically, before I dive into any calculations, I do tend to write them in phasor form as well. And we can kind of do the first two by inspection. The magnitude of A is 4 times square root of 2. So 4 squared plus 4 squared square root. Hopefully we all agree, 4 times square root of 2. Essentially, I'm just plugging them into, there's the real, there's the imaginary, take the square root, real, imaginary, square root, and an angle of 45 degrees, or pi over 4 if you prefer. And likewise, we have 2 square root of 2 here, and an angle of minus 45 degrees. And the last one you can calculate out if you don't believe me, but it's 3.16 with an angle of minus 161 degrees. And I don't care if you write this in radians. I tend to write in degrees just because I can visualize that a little bit better. Then we're asked to do a couple of exercises. Well, one thing to note here, this is magnitude. and this is phase. We've already said that. Magnitude and amplitude are synonymous in terms of this analysis. The amplitude of the sinusoidal wave has a peak value, which is the magnitude of the sinusoidal wave. Doesn't matter where the phase is, where it crosses zero or anything like that. The amplitude and the magnitude are synonymous for our analysis. And so in the very first question, we're asked to find the magnitude of A. Well, that's the real part squared plus the imaginary part squared square root. We already have done that. Another way of writing this symbolically that we'll use would be something like magnitude of A, angle A. And similarly, magnitude of B, angle B, magnitude of C, angle C. And I'll tend to do that periodically. So it's just a representation. We already did the math, or I did the math and wrote it down, and you believe me. Not a safe thing, but. So the very first question we answered, find the angle of B. We already verified that. The angle of B was minus 45 degrees. We can again go back to the real imaginary plot, prove that, or take the inverse tangent. Minus 2 over 2 is minus 45 degrees. And we've expressed C in phasor form, so we've kind of done that already. We can write it also as 3.16 e to the j 161 degrees. Again, that's equivalent. And so now, kind of going on to where we're headed a little bit, A minus B. So that equals something. And this is where we need to be a little bit careful over what form we're using. So A minus B, it's an arithmetic operation, addition and subtraction being equivalent. Well, which of these two forms can I use to do addition and subtraction? So addition and subtraction with regard to complex numbers, or which can I use easily, I should say. We want to use the rectangular form. And we can write this as A real plus J A imaginary minus B real plus J B imaginary. And you collect common terms, so you would collect the real components and the imaginary components. And if I skip down here, this winds up just being A real minus B real plus A imaginary, J in front, minus B imaginary. If I do that math, we wind up with 2 plus J6. And so addition and subtraction, you want to have the form in rectangular form. So if we knew the phasor form, we'd want to convert to rectangular form, back and forth to do addition and subtraction as needed. On the other hand, what if we're doing multiplication or division? Anybody still writing? Everybody good? So if we're going to do something like A over B, well, certainly we could do 4 plus J4 over 2 minus J2. And how would we do this if we didn't have a calculator at our disposal? Well, in order to clean things up a little bit, what you normally do is multiply by B conjugate over B conjugate. That's 1, right? So what effectively I've done is written A over B times B conjugate over B conjugate. And what is B times B conjugate? It's a mumbling, but I'm not sure I heard the right answer. What's that? It's the magnitude of B squared. So that's the magnitude of B. We already know the magnitude of B is 2 times square root of 2. So we can plug that in. We can do a little bit of math. This is not the way to do things, by the way. So if you're busy writing stuff down. This is not how we want to do it. So 4 plus J4, and then 2 plus J2, and then do the complex number out and we'll get some number. That's how we would do it with rectangular numbers, but if we have lots of terms, we certainly don't want to do that. So addition, or multiplication, and division we want to use phasor form. And so in this case, we have A over B, we can write as magnitude A, angle A, over magnitude B, angle B. And so, well, multiplication and division, magnitudes multiply slash divide. Using, I guess we could call them normal math rules. So 4 over 6 would be 2/3, or 0.66. 4 times 6, 24. Normal math rules, elementary school stuff. Whereas angles, multiplication, we add angles. Division, we subtract angles. So these are our rules. So effectively, this winds up being magnitude A over angle, or sorry, magnitude A over magnitude B, angle A minus angle B, because it's division. And we already know what magnitude of A and magnitude of B are. We had them on the previous page. Here they are. 4 over square root of 2 and 2, or 4 times square root of 2 and 2 times square root of 2. So we wind up with 4 square root of 2, 2 square root of 2, angle 45, minus angle 45, minus sign in there. And so we wind up with 2 angle 90. Oops. Effectively, what's 2 angle 90? In rectangular form, what is that? Equals 2J, or J2, however you want to say it. So that's on the imaginary axis, 90 degrees relative to the x-axis. And so an angle of 90 degrees corresponds to J. And so there's our result. But we want to do all the multiplication slash division in phasor form. Now certainly you can go through a mess like this, but there's no reason to. Once you have it in phasor form, it's much easier. For example, if we look at the next one, AB over C. Well, we certainly don't want to have many, many complex numbers multiplying out, so we do this directly in phasor form, and we can write this as 4 times square root of 2, angle 45, 2 times square root of 2, angle minus 45, and then we have 3.16, angle minus 161, and do everything out there. And we wind up with 4 times square root of 2, 2 times square root of 2, which is some number. I think it's around 5. Angle 45 plus minus angle 45 minus angle minus 161 equals something like 5.6, angle 161 degrees. Those guys cancel, minus minus, on. Everybody in agreement? We're going to do this a lot. Something to look forward to. And we will need to walk back and forth between phasor form and rectangular form depending on what we're calculating, how things play out. Okay. So, to go back to the circuit we looked at yesterday, and to revisit that, and as I promised, we'll get very tired of this circuit. Our RC circuit. 1K, 10 to the minus 6, and 2 cosine. I didn't give myself much room. Some numbers to perhaps be a little familiar with. I gave a frequency in this problem of 159 hertz. That's a kind of magical number. Why is that a magical number? Because omega is about 1 kiloradians per second. So 159, good one to recognize multiples thereof. It lets me deal with whole numbers, which is usually kind of nice. So what do we wind up with here? There's our V source. V source then is 2 cosine 1000 t. Now, I made a kind of assignment here, 0 phase. And that's usually what you'll do. The source is the reference phase at 0. So since it's a cosine, we wind up with a nice cosine, semi-nice cosine. And it is for all time. I drew it at t equals 0, but I should be careful. This is AC steady state. It does not turn on at t equals 0. Unlike PSpice, and some of you saw this in PSpice. PSpice does not do AC steady state, which is why you have to wait a few cycles for the changes to split to decay. So there's our source. Hook it up to a function generator or a discovery board. Set the amplitude to 2 volts. Set the frequency to 159 hertz, which gives us 1,000 radians per second. And lo and behold, we would measure this. And now, how do we know what we're doing? Well, in phasor form, Vs is 2 angle 0. We designated 0 phase for the source. To point out again, all our voltages across our resistor, voltage across our capacitor, they will also be cosinusoidal. So I said this at the start, make sure we use the same trigonometric reference. So it doesn't matter if you pick sine here, as long as everything is sine, because our phase will tell us that information. So, what's our impedance of our circuit? Well, again, something we're probably familiar with, but we have ZR equals R. We had ZL equals SL equals J omega L. And ZC was 1 over SC, which becomes 1 over J omega C. So these are the guys we're looking at now, with the caveat that in AC steady state, S goes to J omega. And we know omega is 1,000, we already discussed that. Another way of writing these same things, sometimes or frequently do this. ZR is still R, ZL, of course, J omega L, and ZC minus J over omega C, because 1 over J is minus J. And so if we think about this for a minute, we have negative impedance here, negative complex impedance, negative imaginary impedance. So we have resistive impedance, which is purely real, and we have imaginary impedance that can be negative or positive. So the imaginary impedance in our circuit can be negative or positive. So coming back to our circuit, well, we had omega equals 1,000. R is still 1,000. That was given. And minus J over 1,000. So ZC 10 to the minus 6. Again, gives us a minus J 1,000. This is a nice convenient number. And that's our circuit. So in the AC steady state analysis, our circuit looks like 2 angle 0, 1K or 1,000. And if we were to write this in phasor form, what is that? Well, that's 1,000 angle 0. This is a sine note. And likewise, we have our cap, which is minus J 1,000. And if we were to write that in phasor form, that winds up being 1,000 angle minus 90. Not something that matters right now, but it's worth being able to transfer back and forth fairly quickly to recognize, at least for the basic components, what our magnitudes and more importantly our phases are. So the question now becomes, what's VC? And we did this last class and we did it yesterday, so it's a little bit of a repeat, but VC, by definition, ZC over ZC plus ZR times Vx, our familiar voltage divider. And we can plug in our values. Minus J 1,000, 1,000 minus J 1,000, reverse the order on this bottom here, and 2 angle 0. And I kind of mixed and matched. I have rectangular notation and phasor notation, but in some sense we want to ultimately form magnitude of the numerator, angle of the numerator, magnitude of the denominator, angle of the denominator, times magnitude of the source, angle of the source. And we already have these two guys, 2 angle 0, so we just need to figure out the magnitude of our numerator, which we can do by inspection. The magnitude of J 1,000, I hope we all agree, is 1,000, and our angle is minus 90 degrees. We actually wrote that up there. So 1,000 angle minus 90, and the denominator likewise we can kind of do by inspection. 1,000 square root of 2, angle minus 45, and 2 angle 0. And we already kind of went over how do we do this. Well, this is multiplication and division. We saw a problem that was very, very similar already. We can write this out as 1,000 times 2 over 1,000 square root of 2 times minus 90 angle minus 45 plus angle 0. And the order here doesn't matter. Subtracting the denominator there. And we do all that out and we wind up with something that looks like square root of 2 angle 45 minus. Right? And so what does that mean for us? Well, if we write this out now, that means VC has an amplitude of a square root of 2. We still have cosine of 1,000t because everything has to be the same radial frequency. And then minus 45 degrees. Or since we're in radians now, minus pi over 4. 45 degrees, they're the same. And what does that mean for us? Well, like we saw yesterday, if we draw our source, and again it is AC steady state, there's our source. So there's V source, 2 cosine 1,000t. And what do we wind up with for our capacitor voltage? Well, a lower amplitude and a shifted phase. I'm probably going to draw this very poorly. I tend to do that. Oops. Lower amplitude. And so we have an amplitude of square root of 2, 1.4, and a phase shift of 45 degrees. And arguably, one of the things we can observe here is when does the peak of the capacitor voltage occur relative to the peak of the source? Well, in time, it's after. So when we have a negative sign, this tends to mean lagging. This is something we'll visit a little bit more thoroughly in Unit 4, but it's a good thing to introduce now. Essentially, it means it happens later. So the capacitor voltage lags the source voltage. The peak happens after, in this case, 45 degrees after pi over 4. And I think I missed in my relative ratios, but hopefully you get the idea. And we saw something like that yesterday. Likewise, we can go through and find VR doing a very similar thing. So if we look at VR, well, that's going to be 1,000, or we can write it symbolically first. ZR is ZR plus ZC times VS. In phasor form, we know what all those are. 1,000 over 1,000 minus J 1,000. 2 angle 0. We can do all our similar conversion to phasor form, and we'll wind up with something that looks like square root of 2 angle 45 plus 45. And the fact that they're both angles 45 is an artifact of the fact that they both have the same magnitude. Both ZR and ZC are 1,000 ohms in magnitude, so don't expect this to always be symmetrical. Well, we can again write this as then square root of 2 cosine 1,000t plus pi over 4. And if I attempted to draw that on this above plot, we would wind up with the peak occurring before the source voltage. In this sense, leading. So our phase is positive, we're leading, and you could say happens before. So negative phase means lagging, positive phase means leading.
The peak or a leading happens before the peak of what?
What your reference is. So our source is our reference.
So for a leading phase, it has to peak or before that sort of.
Right. That's right. So ultimately, if we draw things out, we go back to our circuit and say, well, this is our V source is 2 angle 0. VR equals square root of 2 angle 45. And VC equals square root of 2 angle minus 45. And as I promised, all our Unit 1 material comes back. So what must be true about this circuit in terms of Unit 1 concepts? KVL must apply. So if we apply KVL, well, then we have VR plus VC equals V source. And that has to be true, and so square root of 2 angle 45 plus square root of 2 angle minus 45 better be equal to 2 angle 0. We can go and check that. Square root of 2 cosine pi over 4, or 45, plus j sine pi over 4, plus square root of 2 cosine pi over 4 minus pi over 4. Plus j sine minus pi over 4 equals, not enough room, 2 cosine 0, which I hope we agreed is 1, plus j sine 0, which I hope we agree is 0. And we can go through all that math. Cosine pi over 4 is 1 over square root of 2. So we get 1 plus j1 plus 1 minus j1 equals 2 plus j0. And lo and behold, 2 plus j0 equals 2 plus j0. And I have not lied to you. So good news.
Oh my God.
So, and we had to do that in rectangular form. So we were doing addition here. So we had to convert from our phasor notation to our rectangular notation to add the terms. And KVL still applies. And in some sense, KVL also applies if we did square root of 2 cosine 1000t plus 45 degrees, or plus pi over 4, plus square root of 2 cosine 1000t. I mean, you don't have to write this out. I'm just pointing this out. Pi over 4 equals 2 cosine 1000t. That better still hold. Or again, generations of mathematicians have lied to you, which is unlikely. So, but personally, I would rather do stuff in phasor form than to remember all my trigonometric identities, which I always have a hard time remembering. And so this is my preference. If you really like doing trigonometry on a nice, long, quiet Friday night, by all means. So these are all things that apply. So, well, kind of repeated the process in the next part of the problem. We visited same circuit. And this is, gotta be a little bit careful, 2 cosine 10,000 t now. So this is f equals 15.9. A little bit. 1590 hertz. So 10,000 K. And so, well, what's going to happen with our capacitor impedance? As frequency goes up, what does capacitor impedance do? It goes down. So that comes out, again, of our relationships. As frequency increases, capacitor impedance reduces. So as ZC becomes smaller, what do we expect? And we saw this again in the lab yesterday. I mean, look at this. It doesn't matter if this is an imaginary number and this is a real number. The concepts of relative magnitude still applies. When we thought about this in terms of just two resistances, R1 and R2, as R2 became small relative to R1, this is something we discussed many weeks ago, as R2 becomes small relative to R1, it becomes negligible. And that's true here. As this becomes small in terms of magnitude relative to this, even though one's real and one's imaginary, the same reasoning applies. Now there may be phase terms, etc., but the magnitude is going to be smaller. So we expect a smaller voltage drop. And we can go through the math at the end. VC minus J100 over 1,000 minus J100 to angle 0, and we can crunch some numbers there. And I think we get something like 0.199 angle minus 84. So we have a large phase shift per se, but of relatively small magnitude. So about 10% of the overall magnitude. And so that's what we expect. Now on the same token, we had some kind of rules here we can look at. And if I keep increasing frequency, this guy keeps getting smaller, this term is going to get smaller. It's maybe worth noting what's going to happen to this term. So as frequency increases and this gets smaller, where does this go? Minus 90. So this has an upper bound of, or lower bound I should say, of minus 90. This has a bound of minus 90. You're never going to have a shift greater than 90 degrees. And we'll see something similar with the inductor. So this will go smaller indefinitely. This will reach a limit of minus 90.
As the frequency increases?
As the frequency increases. On the same token, if we write this, let's put that there. So let's look at our other similar circuit. We don't do RL circuits enough, so let's look at this one. This is on the next page. That's supposed to be multiplier. So we have a current source, we have an RL circuit, and we can do all our very similar things. We can find IS in phasor form, 0.05 angle 0. That's phasor form. We can walk back and forth. This was 0 phase. Again, it's our reference, it's our source. We don't have to worry about source phase until we have multiple sources. So we can always use our source as 0 phase. At this frequency, well, ZR still is 20K, no change. ZL equals J 2 pi 10 to the 6 times 3.18 times 10 to the minus 3, which by sheer coincidence is J 20K. And so there's our two values. Now, one of the very first things we're asked, this is an I source. We can again go back to Unit 1 concepts. We draw this circuit as I source 0.005 angle 0, 20K, and J 20K. And we can ask, well, what is the voltage across the source? And that was something we did in homework 1 or homework 2, somewhere around there. And if we ask, what is the voltage across the source, what's the only thing we need to know? And there's a few ways of doing it. This is a current source. And if I had more stuff there, what do we need to know? Well, all we really need to know is the equivalent, right? We did that a long time ago. Found our equivalent using circuit reduction, combining resistors in parallel and series, assuming we didn't have any bridges. And so, well, we can do the same thing. Z equivalent here winds up being ZR in parallel with ZL. And so we have 1 over 20K plus 1 over J 20K to the minus 1. And that winds up being something like 10 square root of 2, angle 45. 10K, 10 square root of 2K, angle 45. And it's that straightforward. Now we can apply Ohm's law. VI source equals I source times Z equivalent, all in phasor form. We know that I source was 0.005, angle 0, and we have 10 square root of 2K, probably 10,000, angle 45. And we can do all that out, and we wind up with 50 square root of 2, angle 45. That's the voltage across our source. So again, just taking advantage of phasor math. Once we have our impedances, we do this using whatever relationships are appropriate. We have inverse relationships. We can do that in phasor form as well. Actually, maybe it's worth just looking at that for a second. So, one of the next questions we can ask is, what is IL? Well, having found this, what's the very fastest way to find the current through the inductor? What's that? Yeah, so we already found the voltage across this guy. This is a parallel circuit. It's a current divider. So if we know the voltage across the source, that's the voltage across the resistor, and the voltage across the inductor as well. And so we can go back now. IL is just going to be 50 square root of 2, angle 45, and we have an impedance of 20K, so that's 20,000, angle 90 degrees. Right? Angle positive 90 degrees. And we can do that out. And we wind up with maybe 0.0025 square root of 2, angle minus 45 degrees. And there's our current through our inductor. Now, you can write out in cosine form now as well. 0.025 square root of 2. That's cosine 2 times 10 to the 6th pi t minus pi over 4. And we can note that the current through the inductor is lagging our source current. It's worth noting. And just to remind ourselves of what leading and lagging look like in terms of some relative phase. Now, what's another way we could have done this? So I did this, found the impedance first. I've already said what type of circuit it is. I found the impedance seen by the source, calculated the voltage, divided by the impedance of the inductor to find the inductor current. In some sense, what's a faster way of doing this? It's a current divider. So we could have just gone directly to the current divider relationship. And our current divider relationship winds up being IL equals, let's step back a minute. Let's write it as IL of X, because I know you missed that. And so IL of S is ZL. Oops, not ZL, ZR. ZR plus ZL times I source of S. Right? And ZR is R, and ZL is SL. So I promised these guys wouldn't go away, and I knew you were worried. So this winds up being R over R plus SL. And yes, S is J omega, but we can leave it like this for the moment. Times I source of S. Well, this is a familiar form for us. We've done this. We're masters of it, having taken the second exam. We can rewrite this as IL of S over I source of S. And no, this is our input. So that's our source. Our source is always our input. Am I still on the screen? Sort of. There's our input. So the source is what we control. That's our input to the system. It's fairly logical. Here's an output. Output is what we measure. And it may be what we use to do work for us or whatever. In this case, we're just treating it as a math problem. But there's our output over our input. We can rewrite this as I out of S over I in of S. Input, ratio of output to input. This has a special name. And it's a term we've used before, but we call that H of S, which is the transfer function. And the definition of the transfer function is exactly what you see. Transfer function is the ratio of the output to the input in the S domain. And since this is AC steady state, there are no initial condition terms. So that's good news for us. No IC sources. We don't have to worry about those. So we just have SL and 1 over SC. And our transfer function for the above circuit is already given for us right there. It's R over R plus SL. So I just moved the input to the other side, and we get the transfer function that just depends on the components. Depends on our exceedances in this case. In this case, our transfer function is unitless, but we could have a V out over an I in, or an I out over a V in, in which case we have ohms or mhos, as the case may be. But any of those are possible, but we find the transfer function. Now, looking at this, we can say for this given circuit, IL over I source of S equals R over R plus SL. And if we look at this in terms of behavior, we know S is J omega in our AC steady state. We can take advantage of that knowledge in our transfer function. Looking at this observationally, at the problem we just looked at, we can say IL over IS is R plus J omega L, which was 20K over 20K plus J 20K. And that's the ratio between these. It winds up being a scaling factor. So for a source of 5 milliamps in this case, our output is this times 5 milliamps with no phase. So if this guy has phase, our transfer function has both phase and magnitude. Well, the point here is we can set up the transfer function and we don't have to do the impedance analysis. And we'll do that a little bit more after we take a break. But another thing, we can look at this and make some observational comments. So going back to one of our earlier slides, we've already brought this up a couple of times. As frequency goes to 0, how does an inductor behave? Well, frequency going to 0 is the DC term, so as we go to DC steady state, we know inductors are short circuits, and we see that right here in the expression. Well, looking at our circuit here for a second, as frequency goes to 0, just by inspection, what's the current through the inductor? This we should be able to just look at and say. It's the source current. The inductor is a short circuit. Current follows the path of least resistance. If this is a short, well, all the current's going to go through the short. None are going to go through the resistor. Well, here's our transfer function. Does that tell us the same thing? So as omega, or in this case S, goes to 0, S and omega being equivalent concepts, as S goes to 0, what is our transfer function? 1. R over R is 1. And so, well, if the transfer function is 1, we have an input. What is the output going to be? The input. So our ratio winds up being 1. The input equals the output. And so here's our transfer function telling us exactly what our physical expectations do. So all that Laplace stuff was worth something. If we go back to the other extreme, we kind of made the observation, as omega gets large, and large is a relative term, but as omega goes to infinity, what does our inductor behave as? Well, it behaves as an open circuit. So that's the other extreme. And is that consistent here? So as S goes to infinity, what does our transfer function do? What does our transfer function do? We have R over something going to infinity, and R over anything going to infinity is 0. And therefore, our inductor current is going to what? 0. If this is going to 0 and this is finite, then this guy also has to be going to 0. So our transfer function is consistent with physical expectations. If this is becoming an open circuit, no current's flowing through here, or in other words, the current's going to 0, and that jives with what we just derived. Okay. It's a good time probably to go stretch your legs. There's some eyesores. At what point is ZR negligible? Which is R. Well, if we go back to the unit 1, and we have an R1 and an R2, at what point is R1 negligible? And it's been a while since we've talked about this, but at what point is R1 negligible? What did we say? For R1 to kind of be... Right. So here, kind of ignore R1 when R2 much, much less than R1, right? And we kind of roughly defined what much, much less than was. In this case, you know, I tend to say, well, then R2 less than R1 over 10. Why much, much less than? It's kind of a factor of 10. And mileage may vary depending on what type of setting you're talking about. That's usually a fairly reasonable designation. In some settings, you may have to say 100. In some cases, you can say 3. So whatever the factor is. But, you know, here's a rough estimate of what a scaling factor would be. Well, on the same token, that was unit 1, what must be true for ZR to be negligible? Well, we do need to take into magnitudes because one's imaginary and one's complex, but ZL much less than magnitude of ZR. Magnitude of ZR is just R, so that's a little redundant. And so what are we looking at here? Well, what we're essentially saying is omega L much less than R in this circuit, right? Magnitude of ZL is omega L. Magnitude of a complex or imaginary term is just the imaginary value, J omega L. Magnitude is omega L. And so what can we say? Well, omega much less than R over L. For that frequency range, we can say ZR is negligible. In this circuit, in this parallel circuit. So this is parallel circuits only. And so here's our scaling factor. We can say for parallel circuits, for this parallel circuit, omega less than 1 over 10, R over L, ZR negligible. And so there's a reasonable scaling. So there's a frequency range. Below a given frequency, all we're left with is an IL circuit. And that's essentially what we're saying. So we can do the same approximations that we did in Unit 1, where we have big resistors and small resistors. In this case, a big impedance. In general, a big impedance in parallel with a small impedance. Is approximately Z1 if Z1 magnitude much less than Z2 magnitude. And it doesn't matter what it is, whether either of these are capacitors or inductors or whatever the case may be, or resistors. We compare the magnitudes of the component. If one magnitude is much smaller than the other magnitude for a parallel circuit, here's our approximation. We did this in something similar for just resistor circuits in Lab 2 or Lab 3, I can't remember which one it was. But we compared it, yeah, factor of 10 wound up being a fairly reasonable value. On the same token, if we have something like this, Z1 and Z2, that's approximately Z2 if, same rule, magnitude Z1 much less than magnitude Z2. And so these are things we can look at. Now, what's the difference now that we're talking about L and C? Well, the difference is these magnitudes are frequency dependent. So we do have to look at the frequency, and we can say what that is. For this case, we can ignore ZR for omega small relative to R over L. And so this comes back to the concept that we just kind of looked at with regard to our transfer function that we had up just a moment ago. We looked at the limits. We looked as omega goes to 0. We looked at as omega goes to infinity. But really, what do we care about? Well, if we rewrite this a slightly different way, so we take the same transfer function, IL, and now we'll use J omega over IS J omega. And again, just because I want to drive it home, that's H of J omega, the transfer function, equals R over R plus J omega L. And to rewrite that a little bit, that's R over L, J omega plus R over L. Doing the same type of thing we did before, isolating our S term. And so, well, When is this 1? Well, this is approximately 1 when omega much, much less than R over L. And that's what we just said. So when omega is much smaller than R over L, and we did that just a moment ago, treating it as a parallel circuit, and now we're doing it the same way, looking at the transfer function. If this is true, this term's negligible, and we get 1, and our transfer function says our inductor current is approximately equal to our source current. We get a transfer function 1. And likewise, this approximately equals 0, or going to 0, when omega much, much larger than R over L. And again, we can use a scaling factor of 10 or anything that's reasonable there. So I write this much, much larger than, but you can say that's 10 times, and this is 1 over 10, as the case may be. And so there's the same limit. So rather than having to go all the way to infinity, well, when does it become vanishingly small? Well, when omega is much, much larger than R over L. In this case, R was 20,000 and L was 3 times 10 to the minus 6. So we can, or 3 times 10 to the minus 3, I mean, and we can plug those in and find values. So we can get a frequency range of operation. And where all this comes back to is, what does it mean when we say something's large? So if I asked you what a large frequency or high frequency is, what would you say? What would you say? What do you think a high frequency is? Yeah, a terahertz, sure, but that's qualified. So it's a terahertz in a terahertz system. So if you had a system that was higher than terahertz would be low. So the whole point there is, well, what's a large frequency and a small frequency? It depends on the circuit. So you have to look at the circuit, you have to look at the relative impedances and find out the relative values of the components, translate those to impedances, and that tells you what large and small is for that given circuit. So it's an important thing to recognize. What's large? Well, it depends. Certainly terahertz is large for humans because we're really not working at that frequency yet. But so, if we look at a slightly more complicated circuit, so again, something looks a little similar to a circuit we've seen in the previous unit, but so a little bit familiar. That's L, R2, R1, C, and B source. And for this given circuit, B source equals 5 cosine 4,000 pi. F equals 2 kilograms. And so one of the things we can ask is, what's the voltage across the capacitor? Well, now we have about 5 different ways of finding that out. Some perhaps easier than others. And so, well, this is a phasor analysis problem. If I asked you to find the voltage across the capacitor, what method would you choose? What's a good choice? Well, if everything was resistance, what would you use? If everything was resistors, 4 resistors in that circuit, how would you find the voltage across that middle leg? Can't have been that long. What approach would you use? What's that? Circuit reduction. What are other options? I did two of them, and one was not circuit reduction. Well, circuit reduction and voltage divider, I think are comparable. Yeah, you could do Thevenin. So you're thinking of all the ones that I didn't pick up, or I didn't do. What's another option? What was half of the first test about? What did you have to do on exam one? Many times. Which has another name. KCL, otherwise known as node analysis. And what's our flip side of node analysis? Mesh analysis. So either of those. Those are what I did. Your suggestions weren't bad, I just didn't do them. But they're all approachable. I mean, actually, we can even set them up. So we have a frequency. We can write this in terms of impedances. So Vs is 5 angle 0. There's our source. We can set up your answers as well. It turns out, as luck would have it, this is once again a whole number. And this is also, oops, that's a cap. A whole number, whole list number. On that note, you know, if on the exam you calculated an impedance that winds up being 3,999.9, you know, 4,000 is okay. I see that because I've had people write out like 8 9s. And just, you know, I usually aim for whole numbers, not always, but usually. So if it looks pretty close to a whole number, use that. So, VC. What are we going to do here? Well, there's VC, and we can write this is ZR1, add a little bit of labels here, ZR2, ZC, ZL, just so we can do some symbolic math. And KCL gives, well, no problem there. We can say VC minus V source, which we know is 5 angle 0, all over ZR1. These are all problems. VC over ZC plus VC over ZR2 plus ZL equals 0. So KCL or node analysis, however you want to say it. And so one equation, one unknown. Yes, they're all complex numbers. We can plug that in. We want to calculate something along the lines of VC times 1 over 500 plus 1 over minus J250 plus 1 over 250 plus J250 equals 5 angle 0 or 5 all over 500. Complex number, plug it in your calculator to kind of make the pitch again. If your calculator doesn't do complex numbers, you may want to borrow one from a friend or ask for an early Christmas present, whatever the case may be. I mean, you really don't want to do this stuff by hand. I don't. So finally calculated as complex numbers. A big chunk of the third test will have complex numbers on it. And the fourth test. And the final, I should say. The final, not quiz 4. Quizzes are short relative to the final. So. The final's long. It's up to those 4. So anyway, there's our expression. We can invert that. We can do some calculations there. I have some numbers written down somewhere. So we have the value. DC60, that's about right. About 16 pages. A lot of pictures though, it's good reading. So you plug in the numbers there, do all our phasor math, and you get something that looks like that. So that's approximately right. What else can we do? Well, we could do mesh analysis. So we could do KVL/mesh. In this case, we have 2 loops. Does that matter? No. We go back to the unit 1 concept. we have, ZR1 times I1 plus ZC times I1 minus I2 equals V source. Or minus V source equals 0 is what we usually wrote. So, okay. And so there's the same mesh analysis with impedances. Yeah, they're complex numbers, no big deal. And then we can write ZR2 times I2 plus ZL times I2 plus ZC times I2 minus I1. It's been a while since we've done this, but hopefully it's like riding a bike. We're all still there. And lo and behold, we have a matrix. We could set it up as a matrix. I don't know if your calculators can do matrix form, but MATLAB has no problem. So 500 minus J250, 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 and then 250. Just adding everything up. I1, I2 equals 5, 0. And so again, a lot of systems can solve this for you. Just set it up. And in this case now, what's VC? Solve that for I1 and I2. VC winds up being what? Well, same thing applies. I1 minus I2 times ZC. That's known. You get those guys from the matrix up above. That was minus J250. And that's it. So everything that we did in those first 3 or 4 weeks comes back, except complex numbers. But it's the same method. So how hard could it be? It would be almost impossible to get stuff wrong now, right? On the same token, because you brought it up, yeah, we could do this with Thevenin. Here's a load. So why not? We can set it up. We don't have to carry it through very far. But if we consider ZC our load, well, what do we need to find? Well, the open circuit in this case is what? It's actually not too hard. What's the open circuit? You can say it symbolically. What's the open circuit? Well, you remove the load. What's the voltage between here and here? What type of circuit is it? Yeah, it's VC. But now with this removed, it's not VC anymore. It becomes the open circuit. What type of circuit is this if we remove the load? A little bit more generally. We have it's a series circuit, otherwise known as, it's a voltage divider. So this winds up being ZR2 plus ZL over ZR2 plus ZL. That's these two components. Just putting parentheses in them just to indicate that they were to the right side, times V source. Right? So we can do that. And that gives us V open circuit. And what would our Z Thevenin be? I'm not sure that this is the best way of doing it. I think it's a little bit more math myself, but it was a good suggestion. I liked it. What's Z Thevenin in this case? Maybe it's a good test problem. What's Z Thevenin? Well, what do you do with the voltage source? You short it, and so what are we looking at? We're looking at the impedance between here and here. If I cover that up, impedance between A and B. Well, what do we have? That's ZR1 in parallel with ZR2 in series with ZL. Right? And we can plug in numbers and find values there. And then what are we left with? An RC circuit, which we still have to go back and do analysis on. So I don't think necessarily this was the better method. I probably would have favored node analysis in terms of the most efficient way of getting the solution, but this was a good suggestion. Does everybody agree with what we wrote here? It's been a while since we've seen this. Anybody not sure? Well, Now comes the sad part, sort of the sad part. What happens if I change the frequency? And I want to find the voltage across the capacitor again. What do I have to do? There's a lot of mumbling, but I'm not sure I heard. I didn't hear what anybody said. What do I have to do if I change the frequency? What's that? Well, I have to do all the calculations all over again. Right? Every time we have a new frequency, we got to do new calculations. And you did that in the lab yesterday. I'm sure it was good times. And you'll do it in the lab next week. So every time we have a new frequency, new calculations. We got to go through. We're going to get a new impedance. We got to figure out what our node analysis in this case. Again, I would favor that one, but whatever it is, we have to go through, calculate new values here, plug them in, etc., etc. What's a better approach? What is a better approach? We've already done it once today. What tool did we just kind of introduce? The transfer function. So we want to find VC of S over V source of S. And so, as promised, that algebra was not going to go away. So here's our circuit, or we could redraw our circuit again. Our circuit looks like there's our V source, R1, and you did problems like this in the homework and you enjoyed them tremendously, I'm sure. I think it was one of the master solved problems. And these are Z's as well, but R1 and R2 are the values of ZR1 and ZR2. So, what are we looking at here? Well, this is, I think, going back to what you said, how we need voltage divider circuit reduction analysis. We can write this as ZC in parallel with ZR2 plus ZL, parentheses, all over ZC in parallel with ZR2 plus ZL. That's one way of writing it. But I think I'm going to go back and do our node analysis because we had that as well. So that's one way we can go through, do circuit reduction. It's reasonable. Alternatively, we can do what we just said, VC of S. We had this written out just a moment ago. 1 over ZR1 plus 1 over ZC plus 1 over ZR1 plus ZL equals 1 over ZR1 times V source of S. Those are the same. I can see it a little bit more easily what to do in the node analysis expression, but they're the same expression. And so we do have to go back to the algebra. We do have to go through all those steps. We can write them out. This winds up being something along the lines of VCS. Once I clean it up to get it into a form that's more polynomial, just like we did before, R1, R2C plus R1 plus R2. And a nice simple formula, so things are good. It only took me one step to get there, 2 steps. I can show you my notes. So, going from here to here, I just found the common denominator, wrote things out, collected terms, did stuff like that. And so now comes the little bit of rearranging. We want V source of S, V capacitor of S over V source of S. To get our transfer function, again, we can do a little bit of manipulation. We wind up with 1 over R1 or 2 over LC plus S over C in the numerator, and then an S squared. And this is just getting it kind of our familiar form that we saw before. And so, good times. So it shouldn't be so hard. Shouldn't take more than an hour to do it.